This is the intermediate UKMT Hamilton paper, so it's designed for these years groups here. It's very different to the UKMT regular challenges. It's only 6 questions, but 2 hours long. All the working is marked. It's 10 marks per question for a maximum of 60 marks. I would suggest that you practice on Cayley papers, which are designed for the year below, whatever year group you're in, because they're very similar, but slightly easier, so that's a good tip. And also, just putting down answers, just like in the regular UKMT challenge, which is just multiple choice and you just have the answers and it's marked by machine. This isn't that. Just putting down the answers doesn't mean anything. You need to actually put down some proper logic and answer the question properly and prove things and stuff like that. So yeah, all around a very different challenge, but let's get into it. So it starts off, I think, with probably the most difficult question on the paper. I think this took me well over 30 minutes of real time to do this. So I was feeling a bit deflated about it because it's only the first question. But anyway, so I decided to start drawing a tree for all of the things that can happen here. So you start with a 2, and you can either square or add 1. So let's just draw a tree representing those decisions. So this is, of course, adding 1, this is squaring. And then let's do the same from here. So here we can either square or add 1 to get these. And here we can either square or add 1 to get those. Okay. So currently I have 1, 2, 3, I have 1, 2, 3, 4 roots. But as you can see, this is just going to get much bigger very quickly, right? In fact, it's going to increase by a power of 2 every time because there are 2 decisions for each number. Except when you get to very big numbers, like 256, you can no longer square this because, of course, the game ends when you reach 1,000. So if you square this, you get over that, and that's you don't want to get over 1,000, you want exactly 1,000. So the only thing you can do with 256 is just add 1 a bunch of times. And that's the end of the chain, eventually, when you add 1 enough times to get to 1,000. And I've put this little box here to represent that this is just going to be one chain. There's no decisions to be made here. All you can do is add 1. So this is one option, is to square, 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 and then just add 1 a bunch of times. So 256 was helpful because it was a big number. So now I'm thinking, what's the biggest number, or what's the smallest number that's big enough to do that, essentially? And what you can figure out very quickly is that 31 squared is 961. So therefore, and 32 squared is just over 1,000. So 31 is the last number which you actually still have a choice. 31 can either become 32 or it can become 961. That's the last number for which there's a choice. Every other number after that, you're just going to be adding 1 every time. So here, for instance, the end of the chain is here because all I would do here is add 1 a bunch of times because 81 squared is too big. So this is one option, is to add 1, square, square, and then you just add 1 a bunch of times. But okay, so my kind of goal here is to maybe draw the tree big enough such that I could just count everything, but it's just going to be way too big, isn't it? And this is what I grappled with for a while. And like I said, this did take a while. But what I eventually realized is 6 was a really important number to me. And let me explain why. With the number 5, 5 can do 2 things, right? It can become 25, or it can become 6. And so can 6. 6 can become 7 or 36. But there's something special about 6, which is 5 can become 6, which can become 7 or 36, or 25, which can become 625 or 26. 6 is the smallest number that's big enough such that one of its branches is a dead end. Or not so much a dead end, but finishes the chain. 36 is big enough to not be able to square, so you just add 1 from here. So when you get to 6, and maybe now just imagine that this game, instead of starting at 2, had started at 6, and we'll ignore all the tree above it. Imagine we're just starting at 6. You can either add 1 or square, but squaring immediately ends that branch, right? Because it's just square it and then add 1 a bunch of times. And then 7, you can either square or add 1, but of course when you square, that's bigger than this, so then you just add 1 a bunch of times, and that's just one branch, and so on, right? So 6 is really nice because it doesn't create a horrible tree that goes off in every direction. You just end up with 1 branch going off here, which becomes a single thing, 1 branch off here, 1 branch off there, and so on, all the way until you get to 31, where the sequence ends, because you either square it for this, which ends the branch, because you just add 1 from there, or you add 1, and then you just have to add 1 forever, because 32 is too big to square. So what I decided to do was, okay, again, let's just pretend the game started at 6 rather than 2. How many options are there for 6? Well, there's 1 here, 2, 3, 4, and just count them very carefully. 6 is 1, 7 is 2, 8 is 3 if we count cumulatively. So that the number that you have is always 3 less than this number, 5 less, 6, 1, 7, 2, 8, 3, or is 5 less. So 31 is going to be 26, 5 less, plus the 1 to 27. And so if you start at 6, there are 27 roots to 1,000. And what's really nice then is if you start at 7, you only lose 1 root. So if you start at 7, there are 26 roots, and if you start at 8, you lose 2 roots. So it's just 1 more root than that, so you have 25, and so on. You can just keep going, and at 31, you have 2 roots. And the reason this is super helpful to me is now I can go back to my original 2, draw the tree for a bit, just like this, and now I can say, well, from here, I don't need to draw anymore. From here, there are 27 roots. From here, now 16 is 10 more than 6, so I'm going to have 10 fewer roots, because of course they go up and down in ones. So this is going to have 17 roots from there. This is 19 more than 6, so it's going to have 19 fewer roots, which is 8. This is 3 more than 6, so it has 3 less roots, which is 24. This is 10 more, we've already said, is 17. And 5, now 5 is less than 6, and this pattern doesn't necessarily continue upwards. The pattern started at 6. But here I've got 5, right? And 5 branched off to a branch with 27 roots, or a branch with 8, combined to make a branch of 35. And now all I need to do is add up all of these roots coming off these branches, the sum of the roots, and we get 128 roots. So yeah, that took me a long time, and it's quite a nice question though, so I couldn't be too mad about it. I was very mad though when I got to this question, which took about 30 seconds, and I did it in my head, and I was really confused as to why they would write this in such an order that this question takes so long. Maybe I'm just missing something, maybe there's just a much easier way of doing this, but this question is so easy that why is it question number 2? Anyway, I shouldn't complain, should I? The first thing I'll do is I'll say what fraction of the largest area is shaded. Well, okay, what it's looking for is the fraction that is the amount that's shaded over the total amount. But of course, if I just call the square 1 by 1, the total area is just 1. So that's over 1, and of course that just equals the total shaded. So all I need to do is find out the total shaded area. I don't need to consider fractions or anything like that. And that's because I've labelled these 1 and 1. But I'm not even going to do that. I'm actually just going to work out the white areas and then do 1 take away them to work out all the grey. So how do I work out the white areas? Well, they're both squares, so it shouldn't be too hard. This triangle, this is worth 10 marks. Let's be very clear and try and make sure we don't give the examiners an excuse to mark us down. This is clearly 45 because this is 90 and this is bisecting, which means, and this is 45, which means this is 45, which means this is an isosceles triangle. So that angle is the same. Sorry, length is the same as that one. But of course, this is a square because it says so. This length is also the same. But of course, if this length is the same as this length, that means that they're both a half. So this square has length a half and a half, which means its area is a quarter. Nice and easy. Now this diagonal is 1 squared plus 1 squared square rooted, which is root 2. Of course, we all know the 1 root 2 triangle. So before I do that, though, I'll say that this triangle is also 45 and 45. How do I know that's 45? Oh, because this is 90 because it's a square, so that's 90, so that's 45 there, which means this length is not the same as this one, but it is the same as this one because it's a different isosceles triangle. But of course this is a square, so this length is the same, and then you do exactly the same logic backwards to work out that's the same. So this diagonal is being split into 3 equal parts. The diagonal itself is 1 squared plus 1 squared is root 2, and so the side of this square is root 2 over 3. And of course that means the side of this is root 2 over 3, and so the area is root 2 times root 2, which is 4, which is 2, over 3 times 3, which is 9. And now all I have to do is take the total area, which is 1, and take away a quarter, take away 2/9. However you want to do this, I made all the numbers 36. You eventually end up with 19 over 36 as your total shaded area, which for me is the fraction of the largest square, because the largest square has area 1. Okay, cool. Question number 3 is also quite a nice question, I thought. When you're doing these kind of questions, really when you're doing any questions in problem solving, I always like to get a feel for what I'm doing by testing the smaller numbers. So if I just choose n to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, now I can't go all the way up to 200, right? That will take me way too long. But if I just check out the first 10 numbers, maybe I'll get a feel for what's going on. Now n to the power n, of course, is 1 to the 1, 2 to the 2, and so on. And it's asking which of these are cube. I'll deal with this later, but first I'll just ask which of these are cube. Now that's clearly cube because it's 1. And 1 cubed is 1. This isn't. 4 is not a cube number. This is because it's literally this thing cubed, so of course it's a cube number. This isn't 64. Sorry, that's not 64, is it? It's is it 2 to the 8? So 256. It's not cube anyway, and neither is this. Now this doesn't initially look cube, but it is, because I could write this as 6 to the power 2 cubed, because of course when you use brackets with indices you multiply the indices, so they would make 6. But of course this is just 36 cubed, so this is a cube number. This is not, because you can't do this kind of intelligent thing with it essentially. Now this you have to be really careful with, because you can't do this, like you can't break 8 up into something that has a 3 when you multiply, but the base number you can say is 2 cubed. And then you can, because you would multiply these, if you were simplifying, you can actually just swap them around, because multiplying doesn't care about order, and now this becomes 2 to the power 8, which is, I think, 256, cubed, which is a cube number, of course. So that does work. This works for the same reason this does, because you could break it down into 9 cubed, because 3 times 3 would make this 9 here, and this does not work. So okay, which numbers work then? If we were to continue this pattern further and further, which work? Well, it's pretty clear that multiples of 3 work. Because you could always just break down the indice into 3 times something else and put the something else inside here, and then you just have a cube coming out here. So multiples of 3 always work. Now this isn't a multiple of 3, so why did this work? Well, it worked because the base was cube, right? Because this could be written as 2 cubed, and then I could swap them over. So I think those are the 2 cases, all the way up to 200, for which this is going to work. Multiples of 3 and n being a cube. Notice how the fact that 1 is a cube is why this one works as well, along with this one. Okay, now I think at this point, yeah, I counted how many of those there were. So 3 times 66 is 198, so there are 66 multiples of 3. And there are 5 cubes that are smaller than 200. So in total, there are 70 cases. Why are there only 70 and not 71? Because 3 cubed is 27 and is also a multiple of 3, so you're counting that case twice. So you remove that case and you get 70. It's kind of irrelevant though, that doesn't actually help, because you also need to consider this bit, because it also wants n plus 1 to also be square. So this is kind of irrelevant, but it's nice to practice counting that kind of thing. Okay, so let's do the same thing again. So this will become 2 to the 2, because we essentially just add 1 to both these numbers, and then of course we essentially get the same list, just shifted back 1, so that it finishes at 11 to the 11. Now of course this number is square, because it's literally 2 squared. We're looking for squares this time. This number is not, it's 27, which is not square. This number is, for the same kind of reason as this, we can say this is 2, so well actually we can say it's 4 squared, because 2 times 2 is 4, and then it's just a square number. So that's good. This doesn't work. This doesn't work. Sorry, it does work, of course, because it's you can break this 6 into 3 times 2 and say this is 6 cubed squared, so it's a square number. And so again, the same kind of thing happens as up here, which is just even numbers just work, because you can always break the indice down into something times 2 and then put the something inside and the 2 outside, and then you end up with a square. So multiples of 2 always work. Now, does anything else work? Just like over here, is there one that kind of works anyway? And this is why I like doing it for small numbers, because it helps me to see, well actually this one, I can't break this 9 up into anything times 2, but this is 3 squared. And then I can swap them over, and just like up here, where if the base was cube itself, the number is cube. If the base is square, the number is square. So this actually also works. And this works because it's even, this doesn't. So again, we have 2 very similar rules, which is this will be square if n is a multiple of 2, or if n is square itself. And now we kind of need to cross-reference these 4 rules and say, okay, therefore we need n to be a multiple of 2 and a multiple of 3. In other words, well, actually we don't. I'm getting ahead of myself there, because of course the n shifts, doesn't it, from here to here. So notice the ones that actually both work is when n is 3, and that's because n is a multiple of 3 here, but then when we add 1, it becomes a multiple of 2, because of course an odd number will become even when you add 1. And likewise, this doesn't work, this multiple of 3 doesn't work, because it's even, and when you add 1 it becomes odd, which isn't going to be helpful for the squaring idea. So actually, it seems like the ones that will work are odd multiples of 3. An odd multiple of 3 will work because it's odd here, and it's a multiple of 3, which means it will work. It just needs to be a multiple of 3. But then because it's odd, it becomes even, which is when the square thing works. So okay, how many odd multiples of 3 are there? Well, these are all the multiples of 3, so we just need to halve it. So there are 33 of those. Okay, so 33 odd multiples of 3. When else does it work? Are there any other times? Well, clearly we can see it works for n is 1. So we can say that. There's another case when n is 1. Is there another case here that isn't either of these things? Well, here I can see, look. This is not 1, which I've already counted, and it's not an odd multiple of 3. So why did this work? Well, it worked because n was a cube, and the next one was a square. So it works when the original n was a cube, and it just so happens to add 1 to become a square. However, it also works when the original was a cube that just becomes even when you add 1. Because, and if I write down the cubes, maybe it becomes clear why. 1 adds, we've already counted 1, so I'll cross it out. We've already counted 27. No, sorry. Let's do 8. 8 add 1 is 9, so that works. 27 add 1 becomes 28, which should work, right? Why have I crossed it out? Why doesn't 27 work? Sorry, just bear with me. I'm trying to work out. 27 is a cube. I add 1, it becomes a square, which is 28. And that should work perfectly, because 28 to the power of 28 is definitely going to be square because it's even. So why have I discounted n is 27? Why have I ignored that? I'm confused. I've got these two, which work 8 and 9, and 125, 126, that's 5 cubed, adds to make even. But surely this is a cube. Oh, I've worked it out. Maybe you worked it out before me. I've crossed this out because I've already counted it in my odd multiples of 3. Right? So just be super careful there. This does work because it becomes 28, but I've already counted that. So I'm going to cross it out, and I only get these two new unique solutions. So currently I have 33, 34, 35, 36 solutions. Now there is one more case, and it's the hardest case to see because there are no examples of it up to n is 10. But if I just make all of that a tiny bit smaller and move on a little bit, there is one more case. If you want to, you can think of it yourself. But if this number up here is an even multiple of 3, now normally even multiples of 3 don't work because they add 1 and you get an odd number. But if you just so happen to add 1 that becomes square, then it will still work, like in this case here. So even multiples of 3 that become square when you add 1. Now let's just write down the square numbers. So for example, 24 usually doesn't work because you'd add 1 and it becomes odd, but in this case you just happen to add 1 and it becomes a square number, and so it does actually work. So okay, let's write down all the square numbers, and then take away 1 from all of them, and these are the n's that I'm looking for. Now of course n can't be 0, so I'll get rid of that. We've already counted the 8, 9 case, so I'll get rid of that. This is the one that I just saw, which is cool. This also works because that's a multiple of 3. That's not a multiple of 3, so that doesn't work. That is, and this is 11 squared, so that works. And that is a multiple of 3, that's 13 squared. So I've got 4 more cases here. And so I just need to add these together to make 6, 7, and 40 in total. There are probably better ways to count those all together. It's just a case of really being careful to not overcount doubles like I almost did here, and count this 27 twice. Getting a feel for the problem by using some low examples and helping your brain to figure out the different cases is always a good idea. But yeah, it would have been very easy to miss a couple of cases or overcount a couple of cases here. You would have got nearly full marks if you had gotten like 38, 39, 41 kind of thing, because you only made one small mistake, but the rest of your logic must have been good. So don't worry too much about it, but if you're going for the full 10 marks, obviously you will need the whole thing completely right. Okay, question number 4 is a lovely question. I really enjoyed this. You've got a rectangle, dimensions unspecified, that has area 6. And you're going to put a diagonal through it and create 2 smaller rectangles. And you're told the smaller rectangles have a combined area of 4. And now it says find all possible values for the area of the smallest rectangle here. Or at least smallest in this picture, because the whole point of this is it's kind of telling us we could pick up I and slide it along the diagonal to create different rectangles, like we could slide it all the way up to here to create these two rectangles, and this might be another case where this rectangle plus this one equals 4, and then we'd have a different value for the AEIH rectangle. So okay, that's kind of the premise of the problem. What I decided to do was just look at half of the problem. And the reason that looking at half of it is good is because it's good for a couple of reasons. But the main reason is it means that this triangle here is now very obviously similar to this triangle here. Because of course this angle is the same as this one, they're corresponding, and this is both 90, so these are similar triangles. And I use that a lot here. So what I did was I said, well, okay, this is half the original shape, so the total of this area is 3. The two shaded areas are supposed to add up to 4, so the two triangles therefore add up to 2 of this picture, because it's just half of it. But what's really helpful about that, also, is that means that the white area here is 1. So this is 1, and therefore, because this whole thing is 6 and these are 4, that means this is 1. So it doesn't matter where you slide this point I, both of these right rectangles are always going to be 1 each. Like, they don't distribute that area of 2 in any way that they want. It's always just 1 each, which is really helpful to know. Okay, so the next thing I did was I called the area of the smaller rectangle, or the smaller triangle here, A. And then I said, okay, these are two similar triangles, so pretend there's a scale factor of k from here to here. That means that in terms of area, the scale factor is k squared. Hopefully you've seen scale factors changing across dimensions before. So the area of this one is ak squared. And now I have this new formula that says a plus ak squared is equal to 2, based on this here. And then I've just labeled them down here as well. Okay, so this is one equation with a and k in it. Remember, I'm kind of looking for, I want to find 2a, because I want this thing here. So okay, that's one equation. Can I find another equation linking a and k? Well, what I decided to do was think about, are there any other ways for me to describe the areas of these triangles other than via this similarity idea? And what I did was I said, okay, let's call this length here x, and this length here y. And this length here, I'm running out of letters, so I decided to get fancy and use alpha. And then I'll call this length up here beta. Now, why am I doing all of this? Well, the first thing is that xy equals 1. Because x times y is 1 here, area, and alpha beta equals 1. But also, this gives me another way to describe these two triangles. Because this triangle here, for instance, is it's a triangle, so it's a half, times its base, which is alpha, from over here, times its height, which is x. I'm looking at this sideways. Most of you are probably thinking this area is a half times base, which is x, times height, which is alpha, but of course it's the same thing. And of course this one is going to be a half times its base, which is beta, and its height, which is y. And now maybe you can see what I'm about to do because it is fairly magical, but if I multiply this equation by this one, I'll end up with this. A half times a half is a quarter, and then I'll just end up with all the 4 random letters here. And then this times this is this. But alpha beta is 1, and xy is 1, so I end up with that. And so now I have 2 equations in a and k, and all I need to do is figure out how to eliminate one of the variables to find the other one. Hopefully eliminate k to find a, of course, because a is, or 2a is what I'm looking for originally. Now there are some less fancy ways you could do this than what I think I ended up doing, but I just times this equation all by a, because that means I can just replace that with a quarter, and now this is just a quadratic in a. I think I completed the square to solve this. Yep, I won't talk about this too much in detail. These combine for 3/4, which you move to the other side, you square root. Of course, you get a plus minus when you square root, and then you add 1. Actually, I doubled everything, because remember, I'm looking for 2a. And then I added 2, and the answer is 2 plus root 3 or 2 minus root 3 as my possible areas. So just a really nice question, a really nice combination of geometry and algebra at the end there. So yeah, really, really good. Question number 5 is just algebra. Find all real numbers such that that equals that equals that. So I'm going to break these apart into 2 equations. I'm going to say this needs to equal 2 and this needs to equal 2. And I just stared at this for 30 seconds and I realized there's a very obvious solution. Well, actually, the first thing I thought was, actually, because you're squaring all these things are positive, and they all add up to make 2. So these things are very small, right? Like, for example, if x is even just 2, 2 squared is 4, you're already bigger than this, and these things are positive, so you're not going to get any smaller. So these x, y, and z are all very small. In fact, they're bounded between here, because if it was root 2, that would square to 2, and then you could technically use 0 and 0 to make 2. This wouldn't work, but this is the bound. It's not very relevant, though. I stared at this for another 30 seconds, and I realised there's quite an obvious solution, which is just 1, 0, and minus 1. Because 1 minus minus 1 is 2, and then 2 1s squared with a 0 make 2. So I just realised that and wrote it down. And then I thought, okay, well, I'm obviously being asked for either to find more solutions or to prove that that's the only solution. And I looked at it for another minute or two, and I realised that finding more solutions was exceedingly difficult. So then I decided to just prove that maybe there aren't any more. So what I said was, okay, let's just pretend y is 0, just to show that if y is 0, this is the only solution I can find. So, okay, let's just formally say that y is 0 and solve this simultaneous equation, which is not hard because you rearrange that, you shove that stuff into here, you get a quadratic, which is very easy to solve, and you get one solution if z is minus 1, which of course means that x is positive 1, and that's the solution I found before. So if y is 0, this is the only solution. And now let's think about what happens if y isn't 0. So what I'm going to do is I'm going to very marginally move y to be ever so slightly bigger than 0. It doesn't really matter how far I go. I'm just going to say it's going to be something slightly bigger than 0, or actually something ever so slightly less than 0, because all I really care about is y squared. And of course, when you square something, it always becomes positive. So I'm going to pretend y is either a very small positive number or a very small negative number. So then when I square it, it becomes just a very small positive number, which is just something which I'll call epsilon, which is greater than 0. I'm using epsilon as a bit of an in-joke, because if you do maths at much higher levels, you'll see lots of let epsilon be some number greater than 0. So I'm just kind of using that. But I'm just saying, let's make y just let's nudge it away from 0 in either direction, such that y squared is a very small positive number, and I'll call that number epsilon. And then I'll put that into these equations. Right? So now I'm solving this. But of course, epsilon is just now a constant. It's a very small constant. So I can do exactly the same thing as I did before. Let's rearrange that one, put it back into here, and solve this. And all that changes is you just have these random epsilons around the place. I halved this, which is why I have epsilon over 2. Yeah, I took away 2 from both sides to make a 2, halved it, everything. And now, what I'm going to do is I'm going to look at the discriminant of this quadratic equation, calling this a, this b, and this c. So discriminant is b squared minus 4ac, and if the discriminant is less than 0, there are no solutions. So okay, well the discriminant is 2 squared minus 4 times 1 times this. But of course when I sort that out, I get 4 times 1 is 4, times this one makes a minus 4, and then times this makes minus 4 lots of this, which is minus 2 epsilon. But of course that cancels and you're left with minus 2 epsilon. Epsilon is a positive number, so therefore this is less than 0. So the discriminant is less than 0, which means there are no solutions. So what I've shown here is when y is 0, you have this singular solution, which I found before. And the moment you nudge y anywhere other than 0, there are no solutions at all. Even if you nudge it a tiny bit either way, there are never any solutions ever again. Because you just end up with this negative discriminant here. So yeah, this will therefore be the only solution, and that is the proof of that. Good. Question number 6. I'm going to tell you right now, this question took a long time to animate, and you'll probably see why. Imagine as you're watching this, having to do this in PowerPoint, because it took a long time. So you've got 15 eggs, or 15 boxes, each containing an egg, with 3 rows and 5 columns. All right, so now let's put eggs. My eggs are blue, because why not? Now, he's playing this game where he eats 1 egg a day, and he always wants the remaining eggs to have 2 lines of symmetry. Now, because 3 and 5 are prime, the only possible lines of symmetry here are straight across the middle or straight across the middle vertically. These two. Those are the only possible lines of symmetry. So for that reason, we always need to have those 2 lines of symmetry, because there are no other possible ones to have. So okay, so this clearly works. This has symmetry. So before you take any eggs, it has symmetry. If you remove the middle one, it clearly also has symmetry. Notice, and I'll talk about this more later, but this is actually the only one you can move sorry, the only one you can take out without moving any of the others to still have lines of symmetry to start with. That's kind of interesting. You couldn't remove this one because then this one would be messed up. You could also remove all of the middle though, because this is still symmetrical left and right and up and down. But you couldn't just remove these two, right? Because although this one and this one vertically are now symmetrical, this line is still a line of symmetry, this one isn't because of these two. So you'd have to remove those two as well, and now you have symmetry. Okay, so that's the basic premise. And what he's going to do is he's going to remove one egg per day, and if he removes an egg and there is no longer this kind of nice double symmetry, he's going to move eggs such that he does have it. And he's aiming to make the least movements possible before he runs out of eggs. So first day, you obviously just remove that egg. Easy. You don't have to do any movement. You just remove that egg. Second day, you can remove, say, this egg, or this one apparently. Now this is no longer symmetrical because of the horizontal symmetry is gone, so we'll simply pick this egg up and move it into the middle. And that's one movement on day 2, though I'm not going to keep track of the days very much. Third day, you obviously just remove that egg and you still have symmetry. No movements required. Fourth day, okay, well, what's the easiest way to do this? Removing this egg is annoying because it would break this symmetry because of this egg and this symmetry. So that's actually focusing on these two eggs maybe, because if we remove this one, we only have to move this one into the middle to retain symmetry. So we only have to do one more movement. And then of course the next day we can just remove this egg and we don't have to move at all. Same thing for the next day as well. These two eggs are the best ones because I can remove this one and just put this one in the middle and I retain the symmetry both ways. So that's just one more movement required, just a tally chart being done up here. And next day I can remove the middle egg. Okay, good. Let's keep going. Now we're at the annoying case, right? Because the moment I remove this egg, it destroys this symmetry vertically because of this one and this symmetry horizontally because of this one. So I have to think, well, okay, I'll have to move this one into the middle to save the vertical symmetry, but the horizontal symmetry is still broken because of these two. So what I'm going to have to do is move this one up to here, maybe, and this one up to here. And that's actually the only thing that I can do. I can't just move one of them, right? Because this one requires an egg to be both here and here. So if I just move this one, even if I moved it up to there, I'd be losing it here, and so I'd no longer have it. So I can't just move one, I have to move two. So actually 3 movements were required there. Just going back, I took this one out, a movement was required there, a movement there, and a movement there. So 3 movements were required that day to make my total 6. But now it gets a bit easier because I can just the next day remove the middle one. That's fine. And now the next day after that, again, I've got these two which are nicer because I can just take this one out and then move this one to the center, and that's only 1 movement. So I add 1 to the tally, and then of course I can just take out that one. And now I have the same thing again, right? This one requires this one to be here and this one. So if I remove it, both of these are messed up. So I have to move one of them to the middle, and these two are still messed up. And I can't just move one of them because, again, this one requires one to be here and here for symmetry. And likewise, this one needs one here and here. So I have to move both. So, I mean, there's a few ways you can do it, but the most obvious way maybe is there and there. And now it becomes very easy from here, right? The next day, and that's 3 more movements, by the way. The next day you remove the middle one, then you remove the top one, but put that one in the middle, so that's 1 more movement. And then you finally move the last one. And that's 11 movements in total. And that felt quite efficient, right? It felt like I was doing everything perfectly logical. It felt like I wasn't wasting any steps. It feels like this is probably the right answer. But of course, we mentioned at the start of the video, you don't get very many marks for just correct answers. Maybe if you wrote down every single thing that I said just there out loud in your working, maybe that will get you quite a lot of marks. But let's just formally write down why I think this is definitely, or not even why I think, why this is definitely the least number of things you can use, not just hope it is. Okay, so we'll make a few remarks first. Let's start with 15 eggs here. Now the first day you basically must remove this egg here, because removing any other egg requires a movement. This is the only egg you can move without moving any other. You can remove without moving any of the others. So first day we'll just remove this egg. The other thing we'll remark is if there's an odd number of eggs, you must have the middle egg, right? Now the reason for that is all of these eggs, all of the other ones, every single other egg in the picture has kind of at least one buddy that it's symmetrical with. So for example, this one is buddies with this one. And so this one can only exist if this one does as well. And likewise this one and this one. But the middle egg doesn't have any buddies. Its symmetry is sort of provided by itself. So if there's an odd number of eggs, you must have this egg here, because that's what's providing that odd egg. Literally, this odd egg is providing the odd number of symmetry. Every other one has to be in a pair at least, but that one can live on its own. So if you have an odd number of eggs, on days where you've got odd number of eggs left over, you must have one here. And for the exact opposite reason, I'm not sure what my animation was doing here really, but for the exact opposite reason, on days where you've got even numbers of eggs, you must not have the egg here. Because again, you've got sort of this buddy system which this egg ruins. If you have an egg here, it's not symmetrical with any of the others, so therefore you have an odd number of eggs in total. So on days where you've got even number of eggs, there can't be one in the middle, and on days where you do, there must be one in the middle. So I've written it down here, even if I didn't say it very well. Okay, so those are the remarks we'll make. What I'll also say is, what that essentially means is, there must be a movement from one egg to the middle every other day. Right? Because on even days, what you'll generally be doing is removing the middle egg, because you can't have it if you want an even number of eggs remaining. And on odd days, you must have an egg there, so you must therefore be moving one back into it. So on days where you're going down to an even number of eggs, you're basically just removing the middle one, because it must be there, because you had an odd to start with. And on days where you're getting to an odd number, and you've currently got an even, there's no egg in the middle, so you must be moving one into the middle, because you must have a middle egg on odd days. So every other day, there must be a movement to the middle. Now, how many days is that? Well, you start with one in the middle, so that leaves 14 days remaining. So that's 7 movements by this mechanic of moving one into the middle only to take it away, to move it into the middle again, to take it away, to move it into the middle again, and so on. So there are at least 7 movements, which we'll call the mechanic of just moving them into the center. And then we'll count what are the required movements are there. Well, the other tricky point was when we had situations like this. Let's go over this bit again. Here, I can easily remove this egg, or this one, and just move this into the center. Now that's just this mechanic, right? It's the mechanic from having an odd number from having an even number of eggs right now, to going to an odd number which requires one be put in the middle. So that's just that mechanic. But now we got to this point. We have an odd number of eggs. We have an odd number of eggs right now. So we can just remove this one, that's fine. And now we have an even number again. But again, next we're going to remove an egg which requires one, which means we'll have an odd number left, which means one will have to be in the middle. So when we remove one, we have to put one in the middle. But the problem is that with these eggs, there's just a pair. These eggs are just in a pair. They don't care about any other eggs, right? So when we remove it, we can just put this in the middle, everyone's happy. The problem with these 4, and by extension these 4 on the outsides, the problem with these 4 is they're not in pairs. As I was talking about when I was actually doing it, this egg is not in a pair with this one, it's in kind of a triple with this one and this one. Like it relies on seeing both all the time. And likewise, this one sees both these. So they're actually a quartet by extension. So if you remove one, you've got to put one in the center because you've got an even number of eggs. But this one is also messed up. So it's got to go back into a space where it is paired with another one. So this mechanic, because there's a quartet that rely on each other, you've got to move 3 of them. So this entire step requires 3 movements to retain symmetry. Because of this idea, I talked about when I was actually doing it, but when you remove this egg requires one to be here and here, but you've also required to put one in the center. You can't just move this one to here because then you lose this one and this one needs both. So you've got to get rid of this one completely, which means you've got to get rid of this one as well. So 3 movements are forced here. One of them, be careful, you've already counted. You've already counted the move to center mechanic. That's here. So actually this only increases the minimum number of movements by 2. Then you get to this stage after clearing out these 3, and exactly the same thing happens. You clear out one, you've got to go to the middle, but then you've got to move these two, and so there are 3 more forced movements, one of which is the moving to middle mechanic, which you counted here anyway. So this means another 2 movements are necessary, and so in total 7, 9, 11 movements is the absolute minimum that you could have here at all. And 11 of course was the movements that I found. It's interesting to note that you don't actually need to find a way of doing it like I did. I just showed you straight up the way of doing it. It doesn't actually require you to do that. It just asks what's the smallest number. So if you just skipped all of that and went straight to, oh, there's a minimum of 11 because of this, you would get the full marks. You don't actually need to show any method for actually doing it, which is kind of interesting. But anyway, I hope you enjoyed that video, and I will see you next time.